A bead slides on a smooth, fixed circular hoop of radius r in a vertical plane. The bead is projected with speed root 10 gr from the highest point C. It impinges upon and coalesces with another bead of equal mass at D. CD is the vertical diameter of the hoop. Show that the combined mass will not reach the point C in the subsequent motion. Okay, so the bead C is projected along, it coalesces with this bead, the two of them move up a certain distance. We want to show that the two coalesced beads will not reach the top of the hoop. Obviously we are dealing with a situation of non-uniform circular motion, because the bead is going to speed up actually as it moves down. The first thing that we will do is get the speed at D just before it strikes the second bead. Let's suppose that the mass of this bead is m. We're not given the mass. We are told that D has the same mass. Now, how are we going to do that? Well, notice that the only force that acts on the bead, the only force that has a component in the direction of motion of the bead is gravity, the weight of the bead. Gravity is acting vertically down. It's got a component in the direction of motion, and that's the only force that has a component in the direction of motion. The other force acting on the bead is the contact force of the hoop on the bead, and that's perpendicular to the surface of contact, and hence perpendicular to the direction of motion of the bead. By the way, the direction of the contact force will vary. When the bead is at the top of its motion, the contact force is outward, and as the bead falls down, the contact force is outward. It'll become zero at a certain position, and the contact force will be inward for the rest of the journey. So the hoop will be pressing on this side of the bead. Okay, we saw an example like this in a previous video. But the point is that the contact force does not have a component in the direction of motion. Okay, the contact force is always perpendicular to the direction of motion. So energy conservation can be applied here. So let's get the total energy of the bead at point C. Well, what's its kinetic energy? It's a half its mass m times its speed squared. Well, if we square this, we get 10 gr. Straightforward. What's its potential energy at point C? Well, our reference level now will be where BD is. The height of the bead above this reference level is 2r. So we multiply the mass of the bead times g times the height above the reference level. Now, let's look at total energy of the bead just before it hits the second bead. So its kinetic energy is going to be a half m v squared, where v is the speed of the bead just before it strikes the second bead. We don't know what v is. What's its potential energy? Well, it's mg times its height. Well, that height is going to be 0 just before it strikes the second bead. Now notice that the speed v doesn't depend on the mass of the bead, because the m's cancel out. Okay, solving this, gathering up the grs, we have 7 gr equals half v squared, so v is the multiply by 2 and take the square root. Now next we will get the initial speed of the combined beads. Now we can use conservation of momentum for this part, because just before the first bead collides with the second bead, and just after they collide, there is no force acting in the direction of motion of the first bead and the combined beads. Okay, the forces are always perpendicular to the directions of motion. The weight force is vertically down, contact forces are vertically up actually, the force on the bead due to the hoop. So those forces have no component in the direction of motion, which is this red line here. Okay, this dotted line here. So that means we can apply conservation of momentum in this direction. So what's the momentum just before the first bead strikes the second bead? Well, that's the mass of the first bead times its speed, which is here. That's the momentum before. The momentum of the second bead is 0. Okay, so the direction of motion now is in the horizontal direction. This is just immediately before collision, and immediately after collision, what's the total momentum? Well, the mass is 2m. Okay, the beads have coalesced, and we are interested in the speed after collision. Let's call it v. So mass times speed before, well, that's the total momentum for both beads, equals mass times speed immediately after the collision. So we get V equals root 14 GR over 2. So the combined mass, the 2m mass, has actually half the speed of the first bead. That kind of makes sense. So the mass doubles, but the speed halves to conserve momentum. Now we want to prove that the coalesced beads, they're coalesced now, will not make it up to point C. So how do we do that? Well, we could use a kind of proof by contradiction. We can pretend that the coalesced beads will make it up to point C, and then ask what will the velocity be if they make it to point C. So here we can use conservation of energy, because again the only force that does work on these two coalesced beads is gravity. It's the only force that has a component in the direction of motion of these two beads. So we will get the total energy of the two beads at this position, and then we will consider the total energy of the coalesced beads at the top and equate those energies, and then we can solve for the final speed of the coalesced beads. So this is what we're going to do, and hopefully we will get a contradiction which tells us that we cannot get the speed of the combined beads at C. Something will go wrong. Let's see what's going to happen. So this time we want to get the total energy of the combined beads at point D, that's at the base of the circle, and set it equal to the total energy of the beads at point C, that's at the top of the hoop. So what's the kinetic energy? Well, it's a half times the mass. Well, what's the mass of the combined beads? That's 2m now. What's the speed squared? We have to square this quantity here. Well, that's going to give us 14 GR over 4. What's the potential energy? Well, our reference level is this line here. So the height above this line is 0 when the beads are at point D. So it's the mass 2m times g times 0. Okay, now let's get the kinetic energy at point C. So it's a half times the mass, which is 2m, times v, some v that we're going to try and determine, plus the potential energy. Well, that's the mass 2m times g times the height above the reference level, which is 2r. Okay, so that's the potential energy of the combined beads at point C. So kinetic energy at C plus potential energy at C. Okay, we do a bit of simplifying, and this is where things get interesting. So now we attempt to find the speed of the combined beads at the top of the hoop. This is assuming that the combined beads reach the top of the hoop. Okay, so let's rearrange this to get V. Notice that the answer doesn't depend on the mass, so we can cancel that out. So V squared is going to be 7/2 GR. Well, that's 3.5 GR minus 4 GR. That's going to give us minus 1/2 GR. And this is very interesting, because if we wanted to get the speed V, we would have to take the square root of this quantity, minus 1/2 GR. Now g is a positive quantity, acceleration due to gravity. R is a positive quantity. So clearly minus 1/2 GR is a negative quantity. Okay. So we're trying to get the square root of a negative quantity. So that tells us that we cannot find what we set out to find. We cannot find the speed of the combined beads at C. If we cannot find the speed of the combined beads at C, it means that the combined beads do not reach point C. So this is a nice example of proof by contradiction.